Well, first of all, thank you for coming today, and I'd like to thank Zagier for inviting me to give a talk here. Well, today I'm going to talk about how counting function related to number theoretic object Mach modular form or quantum modular form. So the story begins with Ramanujan's last letter to Hardy. So Ramanujan sent a letter to Hardy, and then he said that he found very interesting function which Ramanujan called Mach zeta function. And then when he said that these functions are beautiful as much as zeta function, and then he just give some example and some property of Mach zeta function without defining what Mach zeta functions are. So I'm beginning with what is zeta function. So Ramanujan's zeta function is a two-variable function. So if we sum negative infinity to infinity by specializing a, b into some special value, where these are some important mathematical objects. So for example, when a, b are both of them are q, then these functions become a classical zeta function. So these type of zeta function are actually a building block of modular forms. So these modular forms are, by mean modular form I mentioned, a complex variable function, so which were holomorphic on a half plane, and then which has some transformation formula, and then it should satisfy some growth condition when heading to the rational number. So the reason these type of modular forms are important in combinatorics or number theory is that for this type of function it has Fourier expansion. So since for many congruent subgroup, there are objects in 1101 matrix, and by the second transformation formula, this implies that the function has a Fourier expansion in terms of Q. And then when in many cases, the coefficients of Q, A of n, having many interesting properties. So that's why mathematicians think about many combinatorics people and number theorists consider modular form to study. So what is good about modular form is that this type of function having, if we fix the weight k and level n, then these type of functions are finite dimensional vector space. So since this is a vector space, there are many operators, or we can expect some structure of the space of this type of function. And then moreover, Ramanujan himself conjectured two important conjectures about tau function. So here the tau n is defined by an infinite product, and then when we expand this infinite product, then nth coefficient is tau n. And then actually this function is a unique weight 12 cusp form. And then he conjectured that this type of function, if we make it as a L function, it has a Euler product, that is a first conjecture. And then the conjecture is solved by Model by the next year when Ramanujan proposed the question. And then the second question is that tau p cannot be large enough. So it should be bounded by some exponent of some power of p. And second conjecture was very deep, and then it was proven by the Lin in 1960s. And then actually these two types of conjecture are some motivation to develop the theory by Haeckel. And then this type of theory enable us that if the function is a modular form, then there are many techniques are developed. So when we have a modular form, then we have many information about how Fourier coefficient A of n looks like. So for example, where I'm going to define I for n as the number of representation of n by sum of 4 squares, then its generating function is actually first power of zeta function. So when we expand first power of zeta function, then coefficients are 1 plus 8 cubed plus 24q squared, blah, 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 blah. Which means that R4 over 2 is 24, R4 over 3 is 32, R4 over 4 is 24. And then, on the other hand, we can think about the other function, which called EG. Then that is defined by 8 times over sigma over n minus 4 times over sigma n over 4. Here, sigma n is a sum of divisors. And then we understood sigma n over 4 is 0 if n is not a multiple of 4. Then this is again where it has pre-exponent of this form. And then when we look at the series, then coefficients of first few coefficients are matched. And then actually these two functions are modular forms of weight 2 when k equals 2 and then level is 4. And then actually the space of modular form of weight 2 and level is 4 over which dimension is 2. So this implies that if the first two coefficients are matched, then the rest of them are matched automatically. So in this sense, E over G has theta to the 4 are same. So this means that R4 over n is the same with sigma 8 times over sigma n minus 4 times sigma n over 4. That was proven by Jacobi several hundred years ago. So in sense of modular form, since it is a vector space, finite dimensional vector space, we can prove it very easily once we recognize the function itself are modular form. So in the literature, where the hardest part is that the function we are looking at becomes a modular form. And then once we have a modular form, then there are many structures in modular form, so we can analyze the coefficients easily. So I'm going to return to Mach zeta function. So Ramanujan says Mach zeta function as he listed 17 examples of Mach zeta function. And then he didn't define Mach zeta function explicitly. Instead of defining Mach zeta function explicitly, he gives some asymptotic behavior of Mach zeta function when intended to some rational numbers. And then he also listed some linear relation between Mach zeta functions. So this is a typical example of a linear relation among Mach zeta functions. So f of q and psi of minus q are Mach zeta functions. And then when we sum of these two, then that is basically square of zeta function and some infinite product. And actually the right side are modular form. So this linear relation suggests that somehow Mach zeta function with similar property of zeta function. So somehow Mach zeta function is related with modular form. And then how they are related was a mystery of in the literature. So among many 17 Mach zeta functions Ramanujan listed, f of q has more attention because the coefficient of f of q has a meaning in combinatorially. And then that serves as a prototype of how their modularity of the other Mach zeta functions are. So in literature, the first connection to the combinatorics is that what is counted by the coefficient. So when we expand the function f of q, then we notice that every coefficient are integer. So when we think about when we look at the integer coefficient, then one of the natural questions is that what is counted by these coefficients. And then that is lead to a question in combinatorics. And the other question is that since f of q Mach zeta functions somewhat look like zeta function, how they what structure they have, that was your second question. So I'm going to answer the first question first. So to this end, I'm going to introduce integer partitions. So integer partitions are partition is a positive integer, is a weakly increasing sequence, and then over which sum equals n. And then since we consider the number as a weakly increasing order, so we do not count the partition in different order or same partition. So we are going to define P of n is the number of total partitions of n, and then P of, for example, P of 4 is 5, because there are 5 ways to represent 4 as a sum of positive integers. And 1920, Ramanujan proved 3 partition congruence, so where the total number of partition of 5n plus 4 is always multiple of 5. And partition number of 7n plus 5 are always multiple of 7. And 11n plus 6 is always divisible by 11. And then when we look at, well, there is no reason we believe there are some pattern in arithmetic of partition functions, but it was a very striking result. And then therefore, and partition function is something combinatorial object, so a natural question is that why P of 5n plus 4 is divisible by 5? Why P of 7n plus 5 is divisible by 7? So people wanted to look at some combinatorial explanation why this type of congruence holds. So in 1944, Dyson introduced a rank of partition. So Dyson defined a rank of partition by the largest number appears in the partition, and then difference between the largest number and the number of appearance as a part. So for example, we have 5 partitions of 4, and then for each partition we can look at the largest number and then the number of parts. So the first partition 4, the rank is defined by 4 minus 1 because largest part is 4 and there is one number. The 4 minus 1 is 3, so the rank of partition 4 is 3. And the rank for partition 3 plus 1 is 1 because the largest number is 3 and we have 2 numbers. And the rank of 2 plus 2 is 0 because the largest number is 2 and the number of parts is also 2. And then similarly, we can calculating the rank for the other partition. And then what Dyson noticed that when we look at the rank in modulus 5, then each weighted class of mod 5 appears only one time. So Dyson calculated the other partition, and then he conjectured that it holds in general. So we define n of I by 5n plus 4 as the number of partitions of 5n plus 4, over which rank is congruence I modulus 5. Then for each weighted class, the number of such a partition is exactly P of 5n plus 4 over 5. That means that for each weighted class, when we think about modulus 5, there are same number of partitions. So if the first conjecture is right, then it is an explanation why the number of partitions of 5n plus 4 is always a multiple of 5. So similarly, when he noticed that it also holds for the partition into 7n plus 5. So when we look at the partitions 7n plus 5 into modulus 7, then he noticed that equally divides the class of partition into same 7 pieces. So that's why P of 7n plus 5 is always a multiple of 7. And then that conjecture is proven by Akin and Swinnerton-Dyer 10 years later using modular form. So when partition rank first introduced to explain Ramanujan's congruence, but surprisingly it is also related with Ramanujan's Maxwell function. So if we define n of mn be the number of partitions of n with rank m, then we can easily find two variable generating function. So in this two variable generating function, if we plug g into -1, then that is same with the Ramanujan Mach zeta function f of q. So when we plug g into -1, then that is the coefficient of q to the n is just a difference between the number of partition of n into even rank and odd rank. So this explains the coefficients of f of q are counted by some partition and then weighted by the parity of the rank. So this is an answer what is counted by the partition Mach zeta function f of q. For structure of Mach zeta function, it has more history. So the first G. N. Watson obtained some transformation formula for Mach zeta function. And then actually these Mach zeta functions are too complicated to understand. And then many years later, Zagier, actually this was a thesis of Zagier, and then he noticed that if we make it pair into a vector valued form, and then if we adding some integration, here f of q is a Ramanujan Mach zeta function, and omega q is the other Mach zeta function of Ramanujan. And then here gi are function of the theta function. So if we add some integration of theta function, and then after adding them, the transformation formula would be very simple. So actually this transformation formula is identical with the transformation formula proven by Watson, but by using the understanding transformula this way, then we can, Brinkman and Ken Ono can find what each component really are. So Zagier shows that we can think that as a vector valued modular form. And then Catherine Brinkman and Ken Ono shows that each component are actually a holomorphic part of harmonic mass form. I'm going to say what is harmonic mass form a little later. And then by understanding harmonic mass form, they can prove that many results about Ramanujan's Mach zeta function. And later, 1 year later, Zagier wrote a survey paper on their results. And then he called such a form as a Mach modular form because it is motivating from Mach zeta function. So what Zagier means by Mach modular forms are there is a Q series, there are some infinite series, and then after adding some integration of theta function, and then if we add them all, then if it become a harmonic mass form, then we say that as a Mach modular form. That was a definition given by Zagier. So harmonic mass form is a kind of extension of modular form. So that is the first requirement is a transformation formula. Then that is basically same with the transformation formula of the modular form. And then previously modular forms are holomorphic function in upper plane. So instead of requiring holomorphic condition, for harmonic mass form requires that it is vanishing by harmonic Laplacian. So that's why from the second condition the name harmonic comes. And then similarly with modular form where it needs certain growth condition. Then if a function satisfying these three conditions, then it also has some kind of Fourier expansion. And unlike modular form, its Fourier expansion has two parts. The one part has an infinite series from some negative number to infinity number. And then the other part is also an infinite series. It's starting from some positive number towards negative infinity. And then we call the first part as a holomorphic part, and then the second part as a non-holomorphic part. So for Mach zeta function, it appears as a holomorphic part of a harmonic Maass form. So by using this theory, where Canono and Catherine Brinkman can prove many results about partition function. And then I'm going to introduce one result using this type of understanding of Maass data function. And then to motivate the question, I'm going to introduce some partition congruence again. And then, well, as I mentioned before, well, Ramanujan proved that 3 congruences of the partition function. And then, well, 80 years later, well, Canono proved that actually there are infinitely many congruences for every prime larger than or equal to 5. And then well, Scott Algren also shows that this is not a coincidence. So well, there are, for every power of prime, there are also infinitely many congruences for partition function. And then Trinius proved that well, this type of thing always happens for large class of modular form. So in this sense, Ramanujan's congruence is not very special. But that kind of congruence happens because the generating functions are actually modular forms. And then these are all, everything about a prime larger than or equal to 5. So our natural question is what happens if we consider modulus 2 or modulus 3. And then actually the long-standing conjecture of Subarao was that there is no congruence for modulus 2 or modulus 3. So unlike the other prime, we cannot expect linear congruence for mod 2 or mod 3. And then very recently, this conjecture proven as true by Sibyl Radu. So there are infinitely many prime larger than 3, but there is no congruence for mod 2 or mod 3. And then we can ask the same question to Maass data function. So for Maass data function f of q, I'm going to say the coefficient by a over n. Then since these Maass data functions are holomorphic part of harmonic Maass form, by using similar technique of trilinear, we can expect that a over n has infinitely many congruence for mod prime power if prime is larger than or equal to 5. So same question is arises. So what happens for mod 2 or mod 3? So for mod 2, the question is trivial because p over n and a over n are congruent because for every partition, rank is either even or odd. So sum over NEN and NON is just P over N. So P over N and A over N are congruent to mod 2. So for mod 3, there are no congruence in general. So we cannot expect linear congruence for mod 3. And then well, this type of theorem also can be applied to class of modular form which we call eta quotient. So here eta function is a Dedekind eta function that is defined by Q3 1 over 24 product sum infinite product. And then when many generating functions in theory of partition are actually an eta quotient. So when we look at the B, here B is when we expand the eta quotient, then the first exponent of the Q expansion is a B. So when we look at the B, then we require 2 conditions. So if we require B is a negative number, and then if B is not a multiple of 2 or 3, then we cannot expect a linear congruence modulus 2 or 3. So this is a very simple criterion when eta quotient can have a congruence mod 2 or mod 3. So for example, so the first one is a generating function for partition function. So generating function of partition function in terms of eta function, it is just eta to the minus 1. And then here B is minus 1. And then minus 1 is not a multiple of 2 or 3. so there is no linear congruence mod 2 or 3. So if we look at the other partition function, so which is the generating function for what we call cubic partition. So for cubic partition, generating function is eta to the minus 1 times eta to the minus 1 over 2g. And in this case, b is negative 3. And then b, for this time, where b is a multiple of 3, and then actually there is a congruence mod 3 for cubic partition. However, that is not a multiple of 2, so there is no linear congruence for mod 2. And then besides of partition rank, there is another partition statistic we call crank of partition. And then for crank of partition, where we can also think about difference between the number of partitions of n with even and odd crank. And then each generating function is also eta quotient. And for this time, b is again minus 1. So there is no linear congruence modulo 2 or modulo 3. So I'm going to give very brief sketch how we can prove the theorem. So basically, the first thing is that when a of n q to the n is a Mach modular form or modular form, then the generating function for arithmetic progression is also Mach modular form or modular form. And then while using transformation formula, then we can actually reduce arithmetic progression. So if b is a coprime to 2 or 3, then we can make m also coprime to 2 or 3. And then using transformation formula of Mach modular form or eta quotient, we can actually calculate one Fourier coefficient at the other cost. And then this gives a contradiction with if there is a congruence for mod 2 or mod 3. So explicit calculation is very messy, but basically this type of result came from transformation formula for Mach zeta function or modular form. So this is how analytic property of the generating function implies some arithmetic property of the combinatorial sequence. So the other question is that in last letter in Ramanujan to Hardy, where Ramanujan says that after reporting he discovering Mach zeta function, he mentioned that unlike pulse zeta function, this has some interesting properties. However, recent study is that this type of pulse zeta function also has some beautiful property. So that I'm going to introduce what kind of property of the pulse zeta function satisfies. So when we say partial zeta function is sum of the form like this, and then here the summation begins from 0 and ends at positive infinity, we call this is a partial zeta function because if we sum negative infinity to infinity, then this becomes a zeta function. So this is just half of zeta function. And then first zeta function is just zeta function like thing. So that is an infinite series. And then, but it has the wrong sign. So if the sign is correct, that becomes a zeta function. So for example, that is a partial first zeta function because instead of 1 minus q to the n, if we have 1 plus q to the n, then this becomes a zeta function. And then this type of functions appears in literature very frequently. So actually it is also related with rank function. So here large n mn is again the number of partitions of n with rank m. Then we can find one variable generating function. A previous generating function was 2 variables. And then for one variable generating function, that is an infinite product times a pulse zeta function. And then this type of thing are useful when we think about how growth of n mn looks like when n goes to infinity for fixed m. And then the other type of identity I want to mention is the Maass identity. Well, this type of identity uses to prove that certain value of a function are integer. And then, well, it has more application in Q-series. And then in combinatorial sense, the reason this type of identity are interesting is that in the left side, there are very few coefficients survive. So there are something only if the exponent of Q is just n squared plus n. However, on the other side, there are many Q. So this type of identity mentioned that in the right side, there will be a numerous cancellation. And then after cancellation, only very few terms are survived. So we can think that the right side is some weighted generating function for some combinatorial object. And then this identity suggests that there are some pairing in the set of the combinatorial generated by the right side. And then we can pair most of them. And then only one object survives when exponent of Q is n squared plus n. And that kind of proof is given recently with joint work with KAIST and Jang-Joo Kim, where he gave a colloquium a few weeks ago. And then, well, today's basically goal is that the structure of partial data function. So again, the story begins with Zagier. And in 2001, Zagier studied some topological invariant, which we call Vassiliev invariant, that is kind of not invariant. And then for this, during studying this not invariant, he noticed that he proved some strange identity. So here f of q is defined by infinite product, sum of products. And then the other side is just something similar which looks like pulse data function or partial data function. The reason this identity is just strange is that f of q is not well defined in everywhere. Well, it doesn't meaningful even in formal power series, because when we expand the product part, every time we have 1, so 1 is infinitely many added. So that is that does not convert for every value of q in the complex. However, that is only meaningful when q is a root of unity. Then when q is a root of unity, then the summation is actually a finite sum. So it has some meaning. So here the equality means that when q is a root of unity, and then in the right side, when we think about the radial limit of q heading to root of unity, then the limit and the special value of fq are identical. So from this, in this identity, Zagier noticed that the right side is actually very similar with Dedekind eta function. So one of the classical results in Q series is Euler's pentagonal number theorem. So according to him, well, eta of g, which is defined as an infinite product, actually having infinite sum expansion. And then for this type of this infinite series expansion, so where the form is very similar. So we have basically in the strange identity, we have n times of chi of 12 of n. So he noticed that we can explain this resemblance by kind of integration of the Dedekind eta function. And then he also noticed that so at the root of unity, then f of q is a transform like a modular form. And then a few years ago, well, he wrote again a survey paper which entitled by quantum modular form. And in this paper, where he defined quantum modular form, so these quantum modular forms are some functions in rational numbers. So previously, modular form is a function in complex variable. So instead of looking at the function in complex variable, he now look at the function in rational number. And then it has transformation like modular form, but little different. So if it is a modular form, then the difference between f of x and slash operator are identically 0 if it is a modular form. But instead of requiring that it's identical, he requires that it has a good property. So in most cases, by good property, he means that it can be expanded to whole real line. So he defined this type of class of function by quantum modular form. And then he lists some examples of quantum modular forms. And then one of the examples appears in his paper in topological invariant. And this type of invariant are actually quantum invariant. So that's why he named this type of function as a quantum modular form. And then this quantum modular form is also appears in combinatorics. So now I'm going to introduce strong unimodal sequence. By strong unimodal sequence, we mean that there is a sequence, and then it keeps increasing, and then there is a peak, notated by C bar, and then after the peak, the sequence becomes decreased. Then if we say that kind of sequence by unimodal sequence, and then we define the weight of a unimodal sequence as sum of number appears in the sequence. And then we also define the rank for a unimodal sequence. So we define the rank by the number of difference between the number after the peak and the before the peak. So therefore, for the unimodal sequence for 5, there is no part before and after the peak, so the rank is 0. And then the unimodal sequence 1, 4, there is one number 1 before the peak, and there is no number after the peak, so the rank becomes -1. And the unimodal sequence 4, 1, then there is one number after the peak, so the rank is 1. And then the other unimodal sequence, we can define the rank similarly. And again, where we can easily find two variable generating function for the number of unimodal sequence with rank m. And then again, when we plug g into -1, something happens. So Canonical proved that when q is a root of unity, and then g is -1, then that is basically same with f of q introduced before. But since that it was introduced by Kontsevich, and then it was a part of strange identity, we now call this function as Kontsevich's strange function. So this means somehow u over -1 is somehow quantum modular form. And then from this, where they prove some claim by Ramanujan, which I did not introduce this talk. So I'm going to introduce in what context quantum modular form appeared in the other combinatorial object. So here I'm going to introduce odd-balanced unimodal sequence. So here, where odd-balanced unimodal sequence is basically strong unimodal sequence, and then we relax some conditions. So where we allow odd numbers in sequence can be repeated, and then the peak must be even, and then the number of odd parts are identical either side of the peak. then the reason we say R balanced is the second requirement, from the second requirement. And then we call this type of sequence by R balanced unimodal sequence. And then there are 16 R balanced unimodal sequence of weight 10. And then we can also define the rank for this rank by the number of parts after the peak, and the difference between the part after the peak and the before of the peak. Then if we define the rank as like before, then each generating function becomes more complicated as compared to strong unimodal sequence. And then, however, it still has some nice properties similar with the strong unimodal sequence generating function. So the first thing is that we can actually classify when the number of whole R balanced unimodal sequence become even or odd. And then from this criterion, we can prove that there are many Ramanujan-like congruence for number of R balanced unimodal sequence. So for example, for given prime added 3, then when 9m plus 1 is always an even number, and when 20m plus 16 is always again even number. And then it also has some quantum properties. So again, when we think about g by minus x by minus 1, and q, if we replace q by 1 over q, then basically the generating function is something looks like a partial theta function. And then this type of partial theta function is that actually quantum modular form of weight 3 over 2, where for this one, it's similarity, as before, similarity, the conservative strange function, it has also quantum modular form, but its detailed properties is a little different. So I'm going to briefly sketch how we can prove the congruence. So basically, by using some 4 power series manipulation, we can actually prove that the coefficients are actually counting the number of ideas. So here, K is a number field Q over square root 3, and OK is a ring of integers. So this means that if we can count number of ideas into over which norm is the congruence 7 modulus 8, then we can actually track the coefficient, the number of unimodal sequence modulus 2. And then we can count the number of ideas by looking at whether the prime is ramified or inert or split in the number field. So we can find the number of ideas in number field, and then that gives a parity over the unimodal sequence. And then from the numerical expansion where we found some conjecture mod 4, and then where the statement of conjecture looks simple. However, the reason I think the proving conjecture is hard is that we have a criterion for the parity of the unimodal sequence according to prime factorization. However, when we know that what we know is some additive condition when we expand the Q series. So we need to pull out information from the additive condition from the multiplicity requirement. So I think that conjecture could be hard. And then for quantum modular form, we can show that basically when x equals minus 1 and q is 1 over q, that is basically pulse theta function. And then that is, we can understand this type of function by Eichler integral of cos theta function. So here Eichler integral means that the periodic integration of the in the bottom. So by looking at Eichler integral, we prove that it has some desirable congruence properties, transformation properties. So in this way where we can prove the quantum modularity for odd-balanced unimodal sequence. And then actually the partition rank and then unimodal rank are actually seems connected. And Ramanujan, without giving proof, where he states the identity connecting the rank of partition and the rank of unimodal sequence. So when this become B becomes minus 1 over A, that become a generating function for partition rank and unimodal rank. And then when A equals B, AB, both of them are -1, then that is a Ramanujan Mach zeta function f of Q. So their generating function is somehow connected. And then here, by complicated function means that that is we call mixed Mach modular form. So this suggests that summing two generating functions become something, some structure. So this gives a hint somehow quantum modular forms and Mach modular forms should be connected. However, so far there is no clear explanation why something happens if we replace Q by 1 over Q. Where sometimes it gives some good properties, sometimes they are not. And then to understand such a thing, where so far where people try to use bilateral infinite sum, but there are no clear structure what happens when we replace Q by 1 over Q. And then there are injection between space of modular forms and space of harmonic mass form, and then space of harmonic mass form and space of quantum modular form. So where harmonic mass form space are larger than modular form space, and then quantum modular form space are larger than harmonic mass form space. So where, on the other hand, when the space is larger, they lose many structure. So we have no structural theorem for quantum modular form space so far. The only thing we know is that if we have a quantum modular form, then when we replace Q by 1 minus Q, then there are some results anticipating the congruence of the coefficient for G of 1 minus Q that was recently proven by very low length. So in general, there is no structural theorem for quantum modular form. So as far as I know, there are two directions. So one direction is using bilateral sum from Q series, and then so far there are some many gaining, but far from the structural theorem. And the other direction is actually traced by Don Choi and Subong Lim, where they use Eichler integral to understand quantum modular form space. Because for quantum modular form that we can think cohomology over the quantum modular form, and then they prove some results using that co-cycle condition, and then they expect some structure from Eichler theory of Eichler integral. But so far, there is no theorem like modular form. So it is nice if we have some structural theorem to understanding quantum modular form, why they are connected with harmonic mass form or modular form. And then it is also nice that what happens when we replace Q by 1 over Q in general. And then thank you for your listening, and that's all I have to say.